today actually we are going to, uh, today in this meeting we are going to complete all the topics, miscellaneous topics which were not covered in the previous meetings. So we will be completing polarization of light waves. We will be completing diffraction of light, then resolving power of optical instruments, and of course we have this topic that is diode as a rectifier from semiconductors. So these miscellaneous topics which are pending from previous sessions, so we will be completing those miscellaneous topics today. Yeah, you're right. You're absolutely right. Actually, polarization has been removed from the syllabus. You're absolutely right. Yes, good evening, Aditya. You're absolutely right. Polarization has been removed from the syllabus. You're absolutely right. Actually, you know that we are having a competitive section every Thursday afternoon, but the problem is that I don't intend to do some chapters again in the competitive section. So I would rather, in the competitive section, I would rather do very big, large chapters. So I am not very keen on doing some portions like modern physics, etc. Like I'm not very keen on doing that in the competitive section. So polarization, you are absolutely right. You are 100% correct. But I'll be doing it so that I don't need to come back to it again in the competitive section, only for that reason. So we'll be doing polarization only for that reason, and we will do diode as a rectifier, which we didn't do earlier. We will do diffraction of light waves. We will do resolving power of optical instruments, and so we'll do that. So these are the miscellaneous topics which we didn't do in the previous sessions. They are left over. So after today's session, the only thing that will be left in this chapter, in our syllabus, the only thing left, I think, will be dual nature of matter and radiation. And perhaps in the radioactivity class, I think we didn't do nuclear fusion, maybe. So I think if that is the case, then we need to do that. So whatever miscellaneous topics we didn't do in previous sessions, we'll finish that off today. So after today's class, the only thing left for us to do will be the chapter dual nature of matter and radiation. Except for that chapter, our syllabus will be over today. So that is what today's session is going to be all about. Okay. So polarization of light. So light is propagating. This is the direction of propagation of light. Okay, light is propagating. This arrow, it gives us the direction of propagation of light. Now, what are these double arrows? Like I have drawn a lot of double arrows. What are these double arrows? So these double arrows, they are basically telling us about the electromagnetic wave that comprises light. Light is an electromagnetic wave. So these double arrows are telling us that the light which is propagating, it is has got electromagnetic vibrations, and those vibrations can be in this plane, in this plane. Basically, you can have infinite directions of light. All of you know that. So the propagation and the vibrations are supposed to be perpendicular, so that can happen in infinite ways. So these double arrows are suggesting that the vibration and the propagation are perpendicular. So now what happens is that these infinite directions of vibration, suppose if we say that these infinite directions of vibration, uh, suppose if we say like this that uh, suppose if we say like this that you consider only the vertical and the horizontal. Okay, just consider the vertical and the horizontal, don't consider anything else, just consider the vertical and the horizontal, and the remaining, like suppose this one for example, okay, or suppose this one for example, so except for the vertical and the horizontal, the remaining of them, you can say that they will, everybody will have a horizontal and a vertical component. So this one, they will all have a horizontal and a vertical component, and the horizontal and vertical component will ultimately just add to this and to this. So that means we can ignore infinite directions and we can just take two directions, vertical and horizontal. We can ignore all the other directions. Now, and this is the direction of propagation. So basically what we do is that whenever we want to show this, suppose the light is propagating, so we just show a double arrow, okay, we show a double arrow and we show a dot over here. Okay, we show a double arrow and we show a dark dot. So double arrow is vibration in one direction and the dark dot is perpendicular to that. So whenever in future we want to show unpolarized light, so this is called unpolarized light. So this is called unpolarized light. So whenever we say unpolarized light, so we say like this, from now onwards, for simplicity, for convenience, we will draw one arrow, so that will show the propagation, and then there will be a double arrow to show the vibration in a particular direction, and then there will be a dark dot here to show the direction in the perpendicular one. Like the double arrow is a particular one and the dark dot is perpendicular to that. So we don't have to show infinite double arrows, right? Now, according to the theory of polarization, there are certain devices, okay, like in isomerism, optical isomerism of organic chemistry, you have studied that there is a nickel cobalt prism, it is called a nickel prism, and then there are some other devices, they are capable of polarizing the light. So what do you mean by polarizing the light? That means that instead of having two directions, one double arrow and one dark dot, there will be only one direction. So that is called polarized light. Okay, now just listen to this. You are passing passing polarized light through a device called a Polaroid. Okay, you are taking polarized light and you are passing it through a device called a Polaroid. Now what is a Polaroid? Polaroid is a device which will polarize the light. The light is unpolarized, it will get polarized. So this unpolarized light will pass through the Polaroid and it will become polarized. So every Polaroid has got something called a pass axis. Okay. So every Polaroid has got something called a pass axis. So this is a Polaroid, so it will have a pass axis. So the pass axis of a Polaroid, what does it signify? So when you have light passing through a Polaroid, then what will happen is that after light reaches the Polaroid, the vibrations which are along the pass axis, only they will be able to go the other way. The rest of them will not be able to go the other way. So ultimately, what will happen? That you will get polarized light. So you have a Polaroid, and those vibrations which are along the pass axis, they will come out of the Polaroid, the others will not come out. So this double arrow represents the vibrations which have been able to come out of the Polaroid. Now what you do is now what you do is you keep a second Polaroid behind the first one. Like this is the first Polaroid, you keep a second Polaroid behind the first one. So this this polarized light, when it passes through the second Polaroid, but the second Polaroid, its pass axis is inclined at an angle to the pass axis of the first Polaroid. So the second Polaroid, the pass axis is inclined at theta to the first Polaroid. And finally, this is how the light will come out. So the first Polaroid is I0, the second Polaroid, it will be I0 into cos square theta. So theta is the angle of inclination between the pass axis of the first and the second Polaroid. So the intensity which comes out of the first Polaroid is I0, and the intensity which comes out of the second Polaroid is I0 cos square theta, and this formula is called Malus Law. Okay, this formula is called Malus Law. So the intensity which comes out of the second Polaroid, that will be equal to I0 cos square theta. This is known as Malus Law. Okay. Now we come to the second law of this chapter, the second law of polarization, that is called Brewster's law. Suppose there is a ray of light which is falling on the boundary between two mediums. So this is the incident ray. Okay, this is the incident ray. It is falling on the boundary of the two mediums. Now this incident ray is unpolarized. Okay, this incident ray is unpolarized. It is falling on the boundary of the two mediums. Now after it falls on the boundary, it will partly be reflected back into the same medium and partly it will be refracted. So partly it will be reflected and partly it will be refracted. So basically what is happening is that you have these double arrows and the dot, so that means this is unpolarized. Now the refracted ray will also be unpolarized, but at a certain angle of incidence, the reflected ray will be polarized. Okay, at a particular angle of incidence, the reflected ray will be polarized. So there was a scientist called Brewster, and he made a discovery that the reflected ray will be polarized when the reflected ray and refracted ray both are perpendicular to each other. So he said that when the refracted and reflected ray are perpendicular to each other, that time the reflected ray will be polarized. So that means this angle will be 90. So I plus R will be equal to 90. So I will be equal to 90 minus R. So R will be equal to 90 minus I. So sin R will be equal to cos I. So I plus R is 90. So R is 90 minus I. So sin R will be cos I. So the refractive index it will be equal to sin I by sin R. So the refractive index mu, it will be equal to sin I by sin R. Okay, and sin R is equal to cos I. So ultimately the refractive index will be tan I. So the refractive index is sin I by sin R. So that is sin I by cos I, and that will ultimately be equal to tan I. So this formula, refractive index equal to tan I, this formula is called Brewster's law. So what is Brewster's law? That at a particular angle of incidence given by mu equal to tan I, the reflected ray is completely polarized. That is called Brewster's law, right? So at a particular angle of incidence, which is given by mu equal to tan I, the refracted ray is completely polarized. This is called Brewster's law. Okay, now we come to the next topic in wave optics, which we haven't done in the previous classes, that is Fraunhofer single slit diffraction. So the next topic in this chapter which we haven't done is Fraunhofer single slit diffraction. So all of you may recall that we have done double slit experiment of Thomas Young, in which we discovered how you have a source of light through which you are getting light rays passing through two narrow slits, and they are interfering on a screen to produce an interference pattern. But in Fraunhofer diffraction, what is happening? That there will be a source of light, yes. So there's a convex lens, the light rays will come out, but there will be only one slit, there will be a single slit. The light will come out of the single slit, and this slit will again be very small. And because the slit is very small, you know what happens, that when the opening is very small compared to the wavelength of the light will not necessarily travel straight. The light may bend around the edges, and that bending around the edges is called diffraction. So the light after entering the slit will bend and it will go and hit somewhere on the screen. So if I consider the middle ray, okay, this is the middle ray. So this bending angle is called diffraction angle theta, and I have taken the top of the slit as A, the bottom of the slit as B, and the middle of the slit as O. So here I have got a triangle. I'll just draw a blow up of this triangle. So this is A, this is O, and I am dropping a perpendicular like this. So suppose this is D. Okay, suppose this is D, and this angle over here, this angle is theta. And from here to here, this is B by 2. Okay, from here to here, this length is B by 2. So automatically from O to D, it will be B by 2 sin theta. Okay, so from A to O, this distance is B by 2. So OD will be B by 2 sin theta. Right? Now, all of you know that this OD is, if you look at the figure carefully, is also the path difference between the two waves, the wave going out of A and the wave going out of O. So B by 2 sin theta if it is equal to lambda by 2, okay, suppose B by 2 sin theta is lambda by 2, all of you know that lambda by 2 is the condition for destructive interference. So if B by 2 sin theta is lambda by 2, then you will get B sin theta equal to lambda. So that means you will get a minima on the screen. Okay. So in Fraunhofer diffraction, the condition to get a minima on the screen is B sin theta equal to lambda. But this I did by taking the ray from O and the ray from A. Instead of that, I can take two rays from any other place, but the distance between them should be B by 2. And if the angle is theta, then like given by this equation, then you will get minima on the screen, a minima, diffraction minima. Similarly, suppose let us say let us say instead of dividing the slit into two equal parts, suppose I divide the slit into four equal parts, and I take the point A and I take the point just below A. So B by 4 sin theta will be lambda by 2. So this will be the condition. So then I will get B sin theta equal to 2 lambda. Okay. So B sin theta equal to 2 lambda. So therefore B sin theta equal to 2 lambda will be the condition for getting a minima on the screen. B sin theta is 2 lambda. So you will get the minima for B sin theta equal to lambda. You will get the minima for B sin theta equal to 2 lambda. if you divide the slit into 6 equal parts, you will get b sin theta equal to 3 lambda. So that means the general condition for minima will be b sin theta equal to n lambda. This is the general condition.
সিক্সের পার্ট থ্রি যেটা আমি একটা ইন্টারনেটে সার্চ করে দেখলাম, ওখানে 100 কিলো দেখাচ্ছে।
So b sin theta equal to n lambda is the condition for getting
আর নাম্বার একটু দেখি
minima on the screen. ছবিটা draw করো। Number 8 ছবিটা draw করো।
ছবিটা পাঠাবো।
যে অঙ্কটা তোমার ডাউট আছে ওই অঙ্কটার একটা ছবি খাতায় ড্র করো। Okay, now this is how the figure will look, the intensity distribution. So y-axis is intensity and this is the x-axis, y-axis is intensity. So the central maximum intensity will be I0. So this is the first minimum. I told you sin theta lambda by b. This is the first minimum on the other side minus lambda by b. The second minimum 2 lambda by b minus 2 lambda by b. And you will notice that successive the maximum, the intensities are reducing. Like the central maximum is I0, but successive maxima, the intensities are reducing. Like compared to I0, this is much less, this is even lesser. So this is going to be the intensity distribution in case of Fraunhofer diffraction. So how does that compare with Young's double slit experiment? In Young's double slit experiment, all the maxima have equal intensity. But in Fraunhofer diffraction, the central maxima is the brightest, but then successive maxima are of lesser intensity, and this graph illustrates the location of the minima, with respect to the maximum. Okay.
আমি রেখেছি।
Okay, suppose there is a convex lens. Okay, there is a convex lens of aperture 2A. Let's say there is a convex lens of aperture 2A and the focal length of that convex length lens is f. So there is a convex lens of aperture 2A, the focal length is f. So what happens is that when we are using an optical instrument, the problem is that the rays which are passing through the lens, instead of coming to a focus, there is a possibility of diffraction. And if diffraction happens, you already know the single slit intensity pattern. So from here to here, okay, from here to here, this central portion, okay, this central portion, its radius is found to be 0.61 into wavelength into focus, focal length divided by A. So 2A is the aperture. So 0.61 into wavelength into f by A. This is the radius of this central portion. Okay, this was the observation made. Now, what happens is that suppose you are using this instrument to resolve two astronomical bodies. So suppose the angle is delta theta. So f into delta theta, it should be approximately equal to 0.61 lambda f by A, because you know that delta theta is the angle into the distance, that should be equal to this radius 0.61 lambda f by A. So delta theta should be 0.61 lambda by A. So this angle delta theta, it should be small. If it is small, the resolution is good. If it is big, the resolution is bad. So that means what? We should have a very large value of A for a good resolution. That means that this lens should have a very large aperture. So the diameter of the objective should be very high. Then only we will get a good resolution. So that is the first thing. So this is for a telescope. and so in a microscope, suppose let us say that the aperture is submitting an angle 2 beta, okay, and at the focus. So capital D is the diameter, the focal length is f, okay, and this is the disk image. The diameter is 1.22 f lambda by d. So this image distance is v. So v theta should be equal to v theta should be 1.22 lambda capital D by d. So this is the minimum distance for perfect resolution. So 1.22 lambda by d divided by magnification. So this v by magnification, this is the minimum distance between the two objects for perfect resolution, right? So this should be equal to 1.22 f lambda by d. So and one more thing, that d by f is equal to 2 tan beta. So this will be 1.22 lambda by 2 tan beta. So that will be approximately equal to 1.22 lambda by 2 sine beta, and if you use a medium of refractive index n, then there will be lambda by n. Okay, so that means what? That we have to ensure the wavelength. Okay, the wavelength is there, and if you put a oil inside the instrument, then the refractive index will be high and this d will be small. So the wavelength should be low, and if possible you should put an oil so that n is high, and therefore the minimum distance for resolution is also very low. So this is the topic, resolving power of optical instruments. তুমি ফিগারটা ভুল এঁকেছো, এটা 25 নয়, এটা 25, ফিগারটা ভুল আছে। সো এটা 25, এটা 30, তো এটাও 30, অল্টারনেট অ্যাঙ্গেল, এটা 25, এটাও 25। এবার এটা 30, এটা 54, তাহলে এটা 96, বিকজ তিনটের টোটাল 180, তো এটা 96। এবার তুমি বাকিগুলো পারবে, বাকিগুলো ট্রাই করো, পারবে। এবার চেষ্টা করো বাকিগুলো পারবে। Okay, then the next topic, we come to diode as a rectifier. We have already done diode earlier. So this is a diode. Okay, this is a AC supply, this is A, this is B. So when B is at a positive potential with respect to A, that time what will happen? The current will flow and you will get an output. But when A is at a positive potential, when A is at a positive potential with respect to B, then the current will try to flow like this, but you will not get any output. So what will happen is that the first half cycle, this is the input, this is the output. In the next half cycle, there is an input, but there won't be any output. So in alternate half cycle, there will be output. There won't be. There will be an input, but there won't be any output, right? So this is called a half wave rectifier. That means every half cycle will give output, the other next half cycle will not give output. So this is called a half wave rectifier. Okay, now if you want to do full wave rectification, so this is a supply, this is the primary of a transformer, this is the soft iron core, this is the secondary. Now in the secondary of the transformer, there is a point A, there is a point C, there is a point B, and what is happening is that in the first half cycle, okay, A is positive. So from A the current will flow like this and it will come to C, okay, but from C the current will not be able to go to B. So this diode will allow the current to go, this diode will not allow in the first half cycle. In the second half cycle, B will be positive with respect to A, so B will send a current to C, that is okay, but C will not be able to send a current to A. So in the first half cycle, this will conduct, this will not. In the second half cycle, this will conduct and this will not. And basically the diagram will be like this. So this will be the input and this will be the output. Okay, so this will be the diagram. So this first one is a half wave rectifier, and this one is a full wave rectifier. So half wave rectifier, the input and output will be differentiated like this, that every half cycle will be missing. And full wave rectifier, the half cycle will appear in the output. So this is half wave rectifier and full wave rectifier, which we hadn't done earlier. Like this completes semiconductor. We have completed wave optics, now we have completed semiconductor. Okay, next topic is nuclear fusion, which we didn't do in radioactivity. Suppose two protons react together, so you'll get a deuterium plus positron plus anti-neutrino, neutrino. Then deuterium plus proton gives He3, and He3 and He3 gives alpha particle. So if you add these three equations, then 4 protons will give 1 alpha particle plus positron plus neutrino plus gamma ray. So this is called proton cycle. This is the example of nuclear fusion. So all of you remember we had discussed this earlier, that radioactivity happens in two extremes. So either the particles, the nuclei are very big like uranium, so it can happen there, or the nuclei have to be very small like hydrogen and deuterium. So if the nuclei are very small, then the two nuclei will merge together to give a heavier nucleus. If the nuclei are very large like uranium, then of course you will have nuclear fission, which we have already discussed. So for light nuclei, they will fuse together to give a heavier nucleus. And in all such cases, the common thing is the mass defect. There will always be a mass defect. So the light nuclei are combining to give a heavier nucleus. So these are all examples of that. And by the way, these three reactions, they are called the proton-proton cycle, and this is the chief source of energy in the sun. So the only problem with nuclear fusion is that the temperature requirement is very high, because the nuclei have to fuse together. So that is only possible when they are in a state of plasma. That means that the atoms do not have any electrons, and therefore they are able to come together and form a heavier nucleus. So the atoms must be able to merge together to form a nucleus. So they are in a state of plasma, and that is how it is happening. So the lighter nuclei, if they are in a state of plasma, then only they will merge together to give a heavier nucleus. But lighter nuclei will only merge together when they are in a state of plasma. That means that the outer electrons are not there at all, and that is how the atoms are able to come together and the nuclei are able to fuse together. So this is the illustration of nuclear fusion, right? So we have completed radioactivity, we have completed wave optics, and we have also completed semiconductors. So whatever syllabus was left of these chapters, we have completed everything. So that means now the only thing left for us to do, there's a chapter dual nature of matter and radiation. That is the only thing left. So in the next session we'll be doing that, and probably we'll finish it in one session, most probably. So that's it for this session. Thank you, and I'll end the session now. Thanks a lot.